So it's a pleasure to be giving the first of the large seminars this year. I'm going to be talking about some recent theoretical work I was involved in on the scattering properties of arrays of nanoparticles. This work is actually very important for the development of quantum technology because many applications like quantum key distribution need the development of better single photon sources. So an ideal single photon source should act as a photon gun. So whenever we pull the trigger, we should get out one photon, exactly one photon, and of the right desired frequency at the right time. To illustrate schematically. So a simple way to model this kind of photon gun is as a two-level system, which we somehow excite to the excited state, ideally using some electrical pumping. And then we allow the excited state to decay by emitting a photon. This will be our single photon that we want. So for this to be a good photon gun, we need that the rate of this radiative transition should be much faster than all other relaxation methods for the two-level system. So we want this radiative decay rate gamma to be as large as possible. And this rate that we have will also limit how often we can fire this photon gun. So the question of how to maximize the radiative decay rate of some transition was solved way back in 1946 by Purcell. So Purcell was studying radio frequency magnetic resonance transitions in atoms, where, as he writes, the normal excitation rate for this process occurs on a time scale which is 10 to the power of 21 seconds, which is somewhat larger than the age of the universe. So something you will never observe. And he had this idea of, okay, what if I somehow have a way to enhance this decay rate by placing the atom in a resonant cavity? And he showed that by doing this, you can enormously speed up the spontaneous emission process from 10 to the power of 21 seconds or down to a matter of minutes. So it's like a 20 orders of magnitude improvement in the spontaneous emission rate. So this enhancement to spontaneous emission is now known as the Purcell effect. And the quantity which describes the enhancement is Purcell factor here, Fp, which basically depends on the quality factor Q of the mode which is resonant with the transition you want to speed up, divided by the volume of the mode. So if we, assuming say that the size of our system is fixed by some constraints, like we want to fit our photon gun in a very small box, then the only way we have to improve the spontaneous emission rate is to increase the quality factor Q. So this is a difficult problem which is attracting interest from researchers all over the world, and even in Singapore, where many people are interested in making bigger and bigger Qs. So the subject of my talk is going to be how we can achieve very high Q factors in using arrays of strongly scattering nanoparticles. So I'm going to begin with a brief review of some of the existing methods for designing high Q resonances in micrometer and nanometer scale photonic systems. I will then review the theory of Mie resonances, which underlies our new results. And finally, our results on how we can engineer high Q collective resonances in chains of nanoparticles. And if you have any questions, please interrupt me. Happy to answer them. Okay, so I'm a theorist. So this is how I would design a high Q cavity. I would take some perfect mirrors and make a Fabry-Perot resonator out of them. Since the Q factor is basically the frequency of the resonance divided by the line width, I can make the line width go to 0 by having perfect mirrors which trap the light, and then the Q factor will diverge. So in practice, we can't do this. The best we can do have highly reflective mirrors based off or distributed Bragg reflectors, which are based off alternating stack of quarter wavelength thick materials. This forms a pretty good mirror in that the reflectivity of each mirror will grow exponentially as you add more layers, at least if you neglect losses due to absorption. So how does this look in practice? Well, here you have quite an old result from 2008, but this is how this can be implemented in practice, where you fabricate a vertical stack of alternating materials to form this Bragg reflector. And in this experiment, they were able to achieve Q factors of 13,000. They also were able to measure the Q factor as a function of the diameter of the pillar. What you can see, and what they mentioned here, is that as they try and make this cavity smaller by decreasing the width of the pillar, the Q factor decreases. This is because even though the Bragg stack is a very good reflector, as you make the diameter smaller, you can have scattering out the sides of the pillar. And so this increases the losses and lowers the Q. So consequently, you can't decrease the mode volume without also decreasing Q. So the Purcell factor they measure is limited to a modest value of about 10, compared to 10 to the power of 20 or whatever Purcell had for his microwave resonator. Here's a more recent result from a few years ago, where to address this side scattering problem, they fabricated a curved Bragg reflector, which allowed them to make the cavity a bit smaller and achieve much better Q values on the order of 1 million, while having a mode volume which is comparable to the wavelength of light. What ultimately limits the performance of this device is that they want to make it smaller to increase the light matter coupling strength. When they try and make this microcavity even smaller, they run into the same problem that smaller cavities are more lossy, which increases the scattering and lowers the Q. Another approach for getting quite large Qs is based off ring resonators. So in this case, what was achieved was a Q factor over 1 billion, which is very good for optics. However, it comes at the cost of having a much larger device footprint. So you see here that the ring diameter is on the order of millimeters, which makes this more useful for classical optics applications rather than having strong coupling to a nanoscale quantum emitter. Again, if you try and make the ring smaller, as they measure here, for smaller diameters, the Q factor is getting lower, which is a consequence of bending losses and sidewall scattering. So again, the Q factor is limited by scattering losses. So a more recent approach for combining high quality factors with very small light confinement is based on photonic crystals, which are 2 or 3 dimensional periodic dielectric media. You can think of these as the higher dimensional analog of a Bragg grating. So the basic idea is that by periodically structuring the system, we can open up a band gap in the modes of the system. So this is a range of frequencies where light will not be allowed to propagate. If we then introduce a localized defect to this otherwise periodic, the light will be localized by the band gap, potentially forming a high Q resonator. So in practice, for the case of 2-dimensional photonic crystal cavities, what they have achieved already several years ago is quite large Q factors, more than 10 million, using this kind of 2-dimensional photonic crystal slab, where they have a defect by removing a few holes. Once again, though, the Q factor is ultimately limited by scattering losses. So in this case, this is a 2-dimensional photonic crystal slab. So even though we have very good light confinement in the plane of the slab, we still have losses due to out-of-plane scattering. This occurs because even though we may have a band gap for the in-plane slab modes, we can always find free space light modes denoted by this shaded light cone region here, which exist at the same energy of the band gap. Therefore, when you break the translational symmetry of the photonic crystal by introducing this defect cavity, you'll break the conservation of the in-plane momentum, meaning you can have scattering processes which couple your guided deflect modes into radiating free space modes. One way this could be addressed is if you could make a 3D photonic crystal, which would confine light in all 3 dimensions. However, this can't be done with current nanofabrication techniques. The required structures are too complicated. So to address this out-of-plane scattering problem, one approach which was becoming very popular in the past decade or so is methods based on bound states in the continuum. But here the idea is that even though your system exists in resonance with free space modes which contribute to losses, if you can fine-tune the geometrical parameters of your photonic crystal, it's possible to suppress this out of radiation using destructive interference. So in this paper here, they show that, okay, if you can, by fine-tuning the radii of the pillars, you can achieve a suppression of out-of-plane scattering corresponding to a bound state in the continuum, which is shown here. You see, in this case, as the in-plane wave vector changes, you have a divergence in the Q factor. So if this sounds too good to be true, it is. So this is theory. Experiment, you don't get infinite Q factor, you get 10 to the power 5, which is a bit smaller. And the authors attribute this lower than the Q factor, not on a problem with the theory, but with a problem with the fabrication. So they say that, okay, even though it may be infinite in theory, probably the fabrication wasn't done very well, sample size. So the theory is great, just the experiment is to get a bit better. Okay. So everything I've shown you seems to suggest that scattering is very bad for designing high Q resonators. If we want to increase the Q factor, we ought to try and minimize the scattering. But actually, it's a bit more complicated questions. So whether scattering can be a good or bad thing really depends on what the scale of your disorder, what the scale of the scatterers is. So if you have scatterers on a very small scale compared to the wavelength, this corresponds to a regime of Rayleigh scattering, where the particle will scatter light in all directions. And this is bad. It seems like it makes it very hard to confine light if it's going everywhere. On the other hand, once you increase the size of the scatterers to a scale which is comparable to or greater than the wavelength, you see that the scattering starts to become very highly directional. This kind of directional scattering can actually be controlled in order to better confine light and give an enhancement to light-matter interactions. So that's what I'm going to be talking about now, how we can use scattering from wavelength scale particles to achieve ultra-high Q factors and very strong per-cell enhancements. Okay, so I'm going to be focusing on this intermediate regime of Mie scattering, which is described by the Mie theory. So Mie theory is the name given to the analytical solution for light scattering of a plane wave of a uniform sphere. This problem was solved analytically by this guy, Gustav Mie, in 1908. So what he did was he basically solved this problem using a spherical harmonic expansion, where he expands the incoming plane wave, the scattered fields, and the internal fields of the sphere in terms of these infinite series of spherical harmonic functions. And if you do so and then apply matching boundary conditions at the surface of the sphere, you get a closed set of algebraic equations which can be solved analytically if you have a lot of time on your hands. So the key thing you get out of the solution are these Mie coefficients A and B, which give you the amplitude of light which is scattered into the different spherical harmonic states. You see that these Mie coefficients take a rather complicated form involving spherical Bessel functions, other nasty things. But this is an analytical result which is valid for arbitrary frequencies of your light. for an arbitrary size of the sphere and for regardless of the refractive index. So even though this is a complicated solution, it gives us a powerful semi-analytical method to understand the properties of light scattering by wavelength scale objects. Moreover, once we have this, once we have the Mie coefficients, we can also we can then explain the scattering spectrum in terms of resonances of different multipole orders. So in particular, the total Q factor of this scatterer, given here by QS, is written as an infinite series of the magnitudes of the Mie coefficients. So you can think of each spherical harmonic as having a resonance with a different Q factor. So here's how it might work in practice. So here on the left, I'm plotting the scattering spectrum for a silicon nanoparticle of 100 nanometer radius. So the total spectrum is shown in black here. And it has quite a complicated structure with many different peaks in the spectrum, with different peak heights, and with what seems quite complicated. But if using Mie theory, we decompose this spectrum into the different multipole orders, the different spherical harmonic functions, actually this can be written as just a sum over a few different multipole resonances. So we have from right to left dipole resonance, magnetic dipole resonance, an electric dipole resonance, and then quadrupole resonances and higher things. So this means that actually the spectrum for this body can be described as a sum of just a few different multipole resonances. The strength and positions of each peak will be sensitive to parameters such as the incoming light frequency, the size of the particle, and its refractive index. So this gives us a tool for manipulating the scattering properties by, say, fine-tuning the particle size. For example, if you tune the electric dipole and magnetic dipole resonances to occur at the same frequency, then this leads to a unidirectional scattering effect, where the particle will scatter light only in the forward direction and not in the reverse direction. So this can be used for designing very thin optical components such as lenses. So this field of manipulating light based off Mie resonant particles is called Mietronics or Mie resonant photonics. And you see recently demonstrated applications micrometer or nanometer scale optical components like wave plates and holograms. Okay, so now we get into new results. Okay, so we want to generalize this Mie theory from scattering by one particle to scattering by many particles. And this becomes a more complicated problem because, say, we have an incoming plane wave. It's the first particle. The first particle will scatter strongly and influence the field seen by the later particles, which will also scatter strongly and influence the field felt by all other particles. So we have a strongly coupled multiple scattering problem that we need to solve in order to get the self-consistent field, which is scattered by the system as a whole. So we can describe this multiple Mie particle scattering using a multiple scattering formalism, whereby we look for a self-consistent solution for the Mie coefficients, the amplitudes of the different multipole components. So this can be written up as the following linear system of equations, where so PL is the magnitude of the nth multipole resonance of the youth particle, and then we say that the field incident on the nth particle is a sum over the field scattered by all the other particles. So what we need now is a relation between the multipole scattering from other particles to the field felt by the nth particle, which we can write as an abstract matrix of coefficients. These coefficients will depend both on the order of the multipole resonance involved, as well as the relative the distance between the two particles. So this seems like a tricky problem. Lucky for us, there was some mathematician who solved it in the 1960s, where he showed that you can exactly relate the multipole scattering from one position to any other position. This result is known as the vector addition theorem, which allows you to convert spherical harmonics in one coordinate system to any other coordinate system. So this solution can be written in closed form, but it's a bit complicated again. He mentions it'd be nice if you could maybe make this a bit simpler, but in 60 years, no one has managed to do so. Lucky for us, though, we have Mathematica or computer algebra systems which allow us to manipulate these very unwieldy expressions for us. And this gives us an expression which can be evaluated exactly for all the elements of the coupling matrix here. If we like, we can also, so this is the scattering from other particles to the nth particles. We're also free to add, say, source terms, for example, due to a dipolar quantum emitter, which is placed in our system at some position RNu. This will act as a source term in this multiple scattering system of equations. So this means that we've reduced this complicated scattering problem to a simple linear system of algebraic equations, which can be solved quite straightforwardly to obtain the amplitudes of the different multipole moments with PL. So once we have the multipole moments of the individual nanoparticles, we can then compute the scattering properties of the system as a whole by performing another multipole expansion about the origin, which is given by this total field expansion here. This global multipole expansion allows us to compute the radiation from this system. So in this case, so once we have the global coefficients obtained again using the vector addition theorem, the Purcell factor is simply the sum of the magnitude squared of the different multipole moments. Okay, so how does this work in practice? So I should mention also that usually the Mie expansion is an infinite series, but to get a finite system of equations, the summation should be truncated to a finite number of multipole moments. And here we compare how well this expansion works in practice for small, which are tractable for brute force numerics based on the finite difference time domain method. So we see here spectra for one particle scattering, two particle scattering. You see the agreement between this multipole scattering theory and the brute force numerics is very good. So this means we have a massive reduction in the computational resources required to study the scattering by these particles. It means that we can go beyond very small systems, which are the only systems which can be studied using FDTT, and look at the properties of large arrays of Mie scattering particles. A second benefit of this approach is that even when the scattering spectra we compute is very complicated, we can get an intuitive semi-analytical understanding of what is happening by decomposing the Purcell factor multipole resonances of different orders. So for the example of this scattering by a single nanoparticle, we see two strong resonances in the spectrum. The first one, the sharper one, is an electric quadrupole resonance. So this corresponds to L equals 2 in the multipole expansion. The broader resonance at the longer wavelength is of a dipolar character. If we now look at the resonances from two nanoparticles, it changes. So now the far field radiation is of a strong dipolar nature, the green curve here, and the quadrupole contribution becomes very small. I'm also plotting here the near and far field profiles obtained from the simulations. What can be seen here is that the dipole, the dipolar emitter, the quantum dot, is placed in a very small gap between nanoparticles, where if we zoom in, there is a very strong enhancement of the near field. So these two ordinary spheres are providing very strong light confinement on the nanoscale, which is responsible for a large Purcell factor. Because this gap is on the scale of nanometers, if you want to study this system using an FDTT method, you need to have a very small grid size in order to resolve these features. But it's quite remarkable that expansion based off the multipoles of the individual spheres is able to reproduce this strong near field structure very well with using a multipole expansion of a relatively low order, I think on the order of 10 multipole terms. So since we can now solve this problem much more efficiently, we can look at how the scattering spectrum depends on the parameters of the system, such as the separation between the two nanoparticles, which is shown in this plot here. So here we vary the separation from 0 to hundreds of nanometers. So you see that the biggest enhancement is obtained for very small separations, for zero separation. This gives you the biggest Purcell factor. Whereas once the separation becomes larger than 100 nanometers or so, the Purcell factor resembles that of a single sphere. So this says that we can get a very strong enhancement of the Purcell factor by having nanoparticles separated by a nanometer scale distance. Okay, let's see what happens as we go to more particles. So here we have spectra for 3, 4, or 5, and 5 particles. You see something very interesting. So as we make our system big, as we make this system bigger, as we add more particles, actually we don't see more resonances. Rather, the quadrupole resonance is getting stronger and stronger with each particle we add. This is very different from, say, a micro ring resonator or a Fabry-Perot cavity, whereas you make the cavity bigger, you get more modes. Here we have an enhancement of the existing modes, in this case, the quadrupole modes of the individual spheres. You also see that the dipole resonance is not being enhanced as we add more particles. It retains a similar Purcell factor. We can continue to make our system bigger and bigger. So here we study 30 spheres. This is extremely hard to do with conventional brute force numerics, because you have to have, say, a resolution of nanometers in the gap, and then the whole computational grid is micrometers or tens of micrometers. But this can be handled quite easily using this multipole expansion. So here we plot the scattering spectra for this 30 particle array for different separations between the particles G, and for a quantum dot placed between two of the particles. So what do we see here? We see that depending on the separation G, we have a few different resonant peaks. Actually, for some values of G, you see some of the peaks disappear. Even though we have, in this case, 30 particles, we only see at most 3 strong resonances from this chain. Again, the number of resonances is much smaller than the geometrical size you would expect based off the known properties of a single particle. If we plot the mode profiles for these 3 peaks, which we call L1, L2, L3, you see that they look kind of like Fabry-Perot modes, and then you have, for the lowest order resonance, it's a single standing wave pattern. And the second mode is a single a single node in the middle. For the L3 resonance, you have two nodes. However, it should be emphasized that these resonances are very different from a conventional Fabry-Perot resonance, because you have losses or scattering losses coming from all over the cavity, not just at the ends. To see better how these peaks are appearing, or merging and crossing, we can plot the spectrum as a function of the separation G. And you see here that as we fine-tune G, the resonance peaks are moving. And first we see that L3 and L2 peaks merge into a single resonance. The Purcell factor is enhanced. As we continue to increase G, the L2 and L1 peaks merge, and you get this huge enhancement of the L1 resonance exceeding 1 million in the Purcell factor. Then increasing G further still, the peaks separate again, and the Purcell factor is lowered. So this is quite remarkable, because we're dealing with a wavelength with of a scale of 1 micrometer. Yet by changing the geometrical parameters by a few nanometers, we see a huge change in the Purcell factor. Because we are dealing with strong scatters with high Q resonances, so this very small geometrical perturbation is getting amplified by the structure. We have a very strong sensitivity to perturbations. So actually this merging and change of the quality factor of the resonances resembles the physics of bound states in the continuum, which I mentioned earlier. It resembles a particular form of BIC called named after these two guys who predicted this kind of phenomena in the 1980s. So here they studied a very simple model of two quantum modes which interact with a shared loss channel. And they showed that as you change the parameters of the modes, such as the detuning between their energy levels, you not only see an avoided crossing in the energy levels here, E1 and E2, as you tune the parameters of this model, you also see an avoided crossing or a splitting of the lifetimes of the individual modes. That's shown by these two plots here, showing the width of the two resonances. So as these two modes undergo an anti-crossing, one of the modes with a broader resonance, that resonance gets even broader, while the width associated with the stronger Q mode gets even narrower. So the Q factor can increase. It can increase to very large values. In this simple model, the width can decrease to 0, corresponding to an infinite Q factor. So it was this study which motivated all these recent works on bound states in the continuum in photonic crystals. All this model and all these other recent works, they consider this model where these two modes are interacting with only one channel of loss. But our system is different because you have many independent loss channels are involved in the scattering processes. So actually, we try and fit our results to a model like this, where you have short-range interactions with a single loss channel. We can do this by taking our multiple scattering model and changing the coupling to near stable coupling between the particles only. So we only allow for near field coupling. If we do this, then we plot the resulting spectrum that's shown in blue here. And you see that this near field coupling approximation fails to capture the resonance of the system at all. You don't get these strong collective peaks. Lower Purcell factor, you just have a single broad resonance, which doesn't relate to what is seen in the actual numerics. Another important difference is as we change the geometrical parameters of the array, which loss channels are important changes dramatically. So for one value of G, which is not subject to fine tuning, if we look at the far field radiation profile, you see many different peaks here. This corresponds to light being emitted at many different angles from the sample, corresponding to many different loss channels. If we fine tune the separation to this special value where you have the very large Purcell factor, the large Purcell factor is not from a single radiation channel being turned off or eliminated due to interference. You still have multiple radiation channels, just the radiation coming out of these channels is a lot stronger than the non-fine tuned case. So this is something which is not captured by conventional fast states in the continuum theory because it always assumes that you have losses via a single channel which you fine tune. Okay, the last thing I'd like to mention is what if we go to even larger arrays? In particular, what if we try and go to the limit of an infinite system, which is then well described by, say, the band theory of photonic crystals? So here we plot the properties of this very strong resonance as a function of the number of particles, going up to 100 particles, which is well beyond the limit of FDTD methods. You can see as we increase the number of particles, the optimal separation, which leads to this very strong resonance, shifts from 1.5 nanometers when you have 20 spheres to converting to a value of about 4.5 nanometers. The wavelength at which this resonance occurs also has a shift from by 10 nanometers or so. As we increase the number of spheres, the strength of the Purcell factor is also increasing. It continues to increase. It does not saturate. So if you were to go to an infinite system size, you would get the infinite Purcell factor, the infinite Q factor. Sorry, you would get the infinite Q factor, which is predicted based off the photonic crystal band structure calculations. And indeed, when you go to the infinite system limit and you compute the corresponding band structure, you see that that this large Purcell factor coincides with an extreme flattening of the modes hosted by the photonic crystal. You get this very flat band emerging, which you can think of as the limit of this very high Q factor collective mode. And one thing I'd like to emphasize here is that because we have these strong shifts in the optimal separation and in the resonance wavelength, even for modest, quite large system sizes of 100 spheres or more, this means that if you try and optimize this cavity, if you try and optimize this nano antenna using a photonic band structure calculation, and then try and apply this calculation to a large but finite system, you will get the wrong result. You will not find the high Q resonance, which is predicted using an infinite system. You really need to be modeling exactly the large but finite arrays of dozens or hundreds of spheres, which this kind of modeling can be done with this multipole scattering theory. So with that, I'm basically done. So as I was saying, so the physics of these mesoscopic arrays of nanoparticles turns out to be very different and gives very surprising results compared to simulations of a few particles or simulations based off an infinite periodic arrangement of particles. If you're using block wave theory, you might get a bad design or the wrong results. And the fact that we can see very strong resonances and very strong Purcell enhancement in relatively simple systems of simple spherical nanoparticles, just with lots of them, offers a novel route towards engineering very strong, very efficient free space quantum emitters. And this is the direction we're currently pursuing in order to see how well this Purcell factor will hold up in an actual experiment. So with that, I indulge my collaborators, in particular, Dr. Pancho Maestar, who did all the calculations, and he's the genius behind this theory. I was involved in more a helping role with Yuri Kipchak at ANU, who is a big expert on me theory and Photonic. And this results in a paper, which is an archive. So with that, thank you, and open for questions.